Hello everyone, welcome back to our class. Let's continuously study Chapter 8, Conduction. In this section, we give several typical examples. Section 8.2, two-dimension steady-state conduction problem. This problem is very famous, very typical. Solving two-dimension steady-state equation is our objective. Most cases we use separation of variable method and difference. The thermal conductivity shape factor. We use shape factor to calculate to some similar calculation. The fourth dimensional rate of heat conduction in this method we usually use. So 1, 2, 3, 4 objective. Solving two-dimensional steady-state conduction equation. This equation is, with just a look, is very simple. Objective certainly is to calculate the temperature distribution. Also, we want to obtain achieving the heat flow density of the medium. So there are two objectives to do this equation, to solve this equation. Two-dimension steady state without heat resource thermal conductivity equation is like this, only two terms, partial t power second over partial x power second plus partial t power second over partial y power second equals 0. So for two-dimension steady state, if there is no heat source, we obtain this equation. If solving the temperature field, it is easy to obtain the heat flow density. So firstly, we want to obtain the temperature field. Like this, here is a two-dimension problem. Here is very simple. Just a look is very simple. How to solve this equation? We should know the heat flow direction is normal to the isothermal surface, isothermal line. For absence of internal heat source and constant property problems, it is converted into a mathematical problem. If in the body no source, no property coefficient change, so the problem is simple. It is converted into a mathematical problem. Different solving methods, certainly we can use different methods to solve the problem, but generally the separation of variable method is most commonly used because this way is more simple, is very common to be used, which can obtain the solution, but only for the simple shape. Most cases, solving the equation is very difficult. But sometimes we can calculate the problem. Okay, how to solve the equation? I said, most cases we use the separation of variables method, and sometimes we use the difference method. Here is the example. Like this figure, we think a heat conduction, it is conduction flat plate. Assuming its three sides keeping temperature in T1, here is T1, T1, and T1. Only the fourth side is T2. Set up the coordinate system. The temperature field certainly is like this: T equals Tx y, function xy. Order, for convenient, we order theta equals T minus T1 over T2 minus T1. Just assume. When we doing this change, we can substitute it into the two-dimensional steady state equation. We obtain the equation like this: partial theta power second over partial x power second plus partial theta power second over partial y power second equals 0. So the equation, the shape just same, but the variable become theta. In this case, the boundary conditions is theta 0, y equals 0. Theta L, y is 0. Theta x, 0 is 0. Finally, theta function x, w equals 1. Only one boundary condition is 1. Using the separation of variable method, so we can order theta xy equals capital X function x, capital Y function y times together. Substitution theta equation, we obtain minus x over x, capital X, times partial x power second over dx power second. It's not partial. Equals 1 over y times dy power second over dy power second. So we obtain this equation. Do some variable separate. This equation can be solved for any x and y when its two sides equals to constant. Order this constant is lambda power second. So we get two equations. So dx power second over dx power second plus lambda power second times x equals 0. And dy power second over dy power second minus lambda power second y equals 0. So we obtained two equations. But these two equations is one dimension. So we can solve it. We can solve them. One partial differential equation becomes two ordinary differential equations. Their general solution I like this, because these two equations is very typical, very famous. So their solution just like this. We obtained x is equals c1 cosine lambda x plus c2 sine lambda x. Lambda power second times y equals c3 e power minus lambda y plus c4 e power lambda y. Here is y and x, the solutions. Under this case, the general form of two-dimensional solutions certainly is times together. So theta xy equals x capital X times capital Y equals these two terms together. Become very long. Here C1, C2, C3, C4 is the integrating constant. We can obtain them from the boundary conditions. We know theta 0 y equals 0. We obtained C1 is 0. From another condition, theta x 0 is 0. We obtained C2 sine lambda x times C3 plus C4 is 0. So we can use the boundary conditions to calculate the integrating constant. Okay, about equation is significant only when C3, C4 together is 0. So we using theta Ly equals 0 obtained C2, C4 sine lambda L times e power lambda y minus e power minus lambda y together equals 0. This is a very special equation. For satisfying this condition and getting useful solution, order lambda satisfy sine lambda L equals 0. Therefore, lambda must be lambda equals n pi over L. Only lambda equals n pi over L, the sine lambda L is 0. In this case, n is 1, 2, 3, many terms. So the solution is a mathematical series. Therefore, the solution can be expressed as this theta equals C2, C4 sine n pi x over L times e power n pi over L y minus e power minus n pi over L times y. Here is very long. The solution C2, C4 is still unknown, but there are two boundary conditions. We do not use it. After combined and use these terms together is 2 sin h n pi over Ly. We use this equation. Finally, we get theta xy equals cn sin n pi x over L times sin h n pi over Ly. We obtain this equation because this term equals 2 sin h n pi over Ly. Step by step. Finally, we get an infinite number of solutions satisfy the differential equation and the boundary conditions. So finally, we obtain this equation. You can find only so simple problem, but the solution is so long, so the solution is generally the solution is very difficult to obtain. For determine Cn is still an integrating constant. The last boundary condition is used. We use this boundary condition. It's the last one. To solve the integrating constant generally is difficult, but mathematics can get the final solutions. They are Cn certainly is very difficult. Cn from the mathematical we can obtain, but generally is very difficult. So the final solution of problem finally obtained like this. Many terms is a series of mathematics. So only this two-dimension problem is very difficult. So generally the conduction is very difficult to obtain the solution. Okay, the final solution is a convergent function. The isothermal and equal heat flux lines can be drawn in this picture. So you can find many terms, and many isothermal lines. It is found this line is symmetrical about x equals L over 2, half L, which is a chordal. We understand about this heat transfer. Okay, from about several pages, we discuss two-dimension steady-state heat conduction. We find generally solving more dimensions steady-state heat conduction problem is very difficult. Generally, it's difficult. However, for some typical shaping factor can be used to solve the function. Just to say, generally it's very difficult to solve the conduction problem, but we can use shape factor and heat conduction rate, dimensionless heat conduction rate to solve some typical problems. So in this section, we discuss thermal conductivity shape factor and dimensionless heat conduction rate. Just to say, in the practical field, we often meet the problems like this. For example, the horizontal cylinder buried in the semi-infinite medium. For example, vertical cylinder buried in the semi-infinite medium. Horizontal cylinder buried in the square medium, like this. Many problems like this. Certainly, to solve the conduction equation is difficult. But this kind of problems is very typical, so we can use the shape factor method to discuss them. For typical shapes, we order the heat conduction rate can be expressed as follow equation, just times a shaping factor. For example, we order the heat flux Q equals S lambda delta T1 to 2. Delta T1 to 2 is the temperature difference. The capital S, is the shaping factor. Certainly, lambda is the conductivity. Most cases, we can use this equation to calculate the solution. So the resistance of two-dimension heat conduction is expressed like this. 1 over S lambda is the resistance only for two dimensions heat conduction. So here is the resistance. Institute this equation like this. So generally, it is still difficult to get the shaping factors. Certainly, the shaping factors is still very difficult to obtain. However, many typical shaping factors have been obtained because heat transfer is a relative older science. Many years. We can check the table to find them. For example, next table just is some typical shaping factors like this. Some typical shaping factor, we can check this table, we can obtain. If we understand, we know the typical shaping factors, the heat flow rate is solved by next function. For next function, Q equals S lambda delta T1 to 2. Lambda is conductivity. Delta T1 to 2 is the temperature difference. Only S is the shaping factor. So we can check this picture, this table, to obtain S, the shaping factors. Shaping factors can be used to solve some typical shape problems. Here, this section we discuss dimensionless heat conduction rate. For isothermal body, buried in isothermal medium, dimensionless heat conduction rate can be used to solve the function. For infinite medium, the characteristic length is defined as like this. LC is AS over 4 pi together power half. AS is the surface area of the body. Dimensionless heat conduction rate from the body to the medium is written as like this: Q psi SS equals Q LC over lambda AS times T1 minus T2. Here is the dimensionless heat conduction rate. When we understand dimensionless heat conduction rate Q sin SS, the real heat conduction rate Q will be calculated by this equation. Q equals Q psi SS lambda AS times T1 minus T2 over LC. We can use this equation to calculate the real heat flow rate. Fortunately, Q psi SS is similar for very broad geometrical shapes. Approximate Q psi SS can be gotten by interpolation method. Dimensionless heat conduction rate of typical problems, mostly we can check them from this table. Okay, it is noticeable the shape factors and dimensionless heat conduction rate is only for uniform temperature bodies and medium. For a body with an equal heat flux or an isothermal body, the lowest temperature place is often on heated boundary. So a more approximate approach is to take a calculation temperature difference of using S and Q psi SS. That is, delta T1 to 2 is average T1 minus average T2. That's to say, the mean temperature difference of the body and the boundary should be taken. So we use the average temperature difference to calculate delta T1 to 2. Okay, here is example. It's very typical sample. Just to tell us one cylinder line cover shelf. This example is very typical. We can, for saving the time, you can study it to understand it by yourself. Here is the solution process. You can study it by yourself. Thank you.